Good afternoon. This is Ian Ding. I'm a research civil engineer at U.S. Army Corps Engineering Development and Research Center, Coast and Hydraulics Lab. Uh, Welcome to our GenCade, it's a shoreline evolution modeling webinar. We're going to have a 2-hour long webinar, and we'll give two presentations. May not even split the time. The first is this introduction to GenCade. Instructor is Mr. Rusty Pointer, and follow that. We're gonna have probably 5 minutes of break, and then I will give a second presentation, mostly focus on those practical issues using GenCade. With this short period of time, we may not have a chance to do the tutorial demonstration, but we would encourage you just we have a next workshop in November, so we'll send the notice later on. That time we will have a whole day to do this training workshop. And so I put a request on the chat. I saw people keep coming. Appreciate that. Would you please put your name and the organization company so we can keep recording your contact information? Thank you. So without further ado, Rusty, would you please start?
Thanks, John. I'm Rusty Permitter. I kind of am on the GenCade team. Anyway, so I'm just going to go over basically the intro to GenCade and kind of the previously, or the basics of the model. I'm going to go over what GenCade is, the background of the model, what the capabilities are, the limitations and assumptions, some of the basic model theory, the workflow, the input and output required of the model external to SMS, and then GenCade with an SMS. And then I also have a slide or two about the Monte Carlo application of GenCade that Jan has been developing over the past several years. GenCade came about as a combination of the two existing tools, Genesis and Cascade. It is the explicit formulation of Genesis, and it combines the two tools to add the features from Cascade, such as like little inlets, shoals, barrier islands. To Genesis, the typical resolution of Cascade was about 500 meters. It was more of a planning tool for regional sediment management. Genesis was more of a engineering design tool. You can get any kind of structure, you can groins, jetties, seawalls, and it had a much, since it's doing such a more refined job on local engineering, the resolution is 25 meters. So the strategy that was used was to add Cascade capabilities to Genesis to get GenCade. Again, so the goal was to integrate both planning and engineering, and you have time scales anywhere from a year to 100 years. It has functionality to allow you to conform to regional trends. And then you can add, like you can represent cumulative effects of local projects, so nourishments or dredging events, inlet bypassing. Over the course of again, a 50-year, 100-year span with engineered elements in place. We also have variable grid resolution for increased accuracy while maintaining computational efficiency. So here's just kind of an overall view of the various processes that are included in GenCade. So we have, the basics of it are longshore transport. We can address groins, jetties, the shoaling at inlet, dredge events, uh, uh, yeah, and break, as well as breakwaters. Uh, so again, the model is applicable across either a regional scale or a local scale. For regional sediment management, you can evaluate beach fills, inlet bypassing, or channel maintenance. On a more local scale, you can do coastal structures, so breakwaters, groins, T-groins, jetties. Um, so more functionality was inlet bypassing. We have the inlet reservoir model, which calculates the transmission of sediment from the various shoals features, as well as the inlet to either side of the inlet. We can add, and this was a pretty frequently, or well, this is a frequently used tool for Genesis, but we can add multiple wave input forcing locations. So if you want to use external wave modeling, so like if you wanted to use ST wave or CMS wave, you could apply that forcing to the GenCade modeling to get the effects of a change in bathymetry on the local shoreline. We can represent coastal structures such as groins, jetties, seawalls, T-head groins. You get salients and possibly tombolos behind the breakwaters. And then we have some of the other, we have multiple methodologies on the breakwaters. We have RNs, and you have just a steady state, like a transmission coefficient. And the wave breaking is calculated internally to the model. We have diffraction routines for the groins. The assumptions of the model are that the beach profile maintains a pretty constant average shape. Longshore transport only occurs between the top and the berm and the depth of closure. So basically, like we're conserving mass. Sand transport is not affected by nearshore current patterns, and that there is a long-term trend in the shoreline evolution for the area. So the longshore net volume change is the change in the flux, or change in the volume the sediment transport multiplied by the cell width times the time. And then the cross-shore volume is just the flux time, or the delta of the flux, or the transport times the time in the cross-shore. And so then you get the total volume change is your, basically your dxdy times the berm height plus the depth of closure. And it's all basically just based on the Cirque equation. So you have our Q is equal to the square of the wave height times the wave group speed, and all times A1 sine of twice angle braking minus A2 cosine of the angle braking times the change in, or the partial differential of the wave breaking height, like in the longshore direction. Then K1 and K2 are really the critical parameters that are used to calibrate GenCade. The K1 value controls the magnitude of the longshore transport rate. The K2 value controls the distribution of the transport rate. And then so typically we use a value of K2 that is between half and 1.5 times the value of K1. And please ask any questions. I hate to get to the end without anybody, if anybody's confused. The inlet reservoir model is pretty straightforward. It just, you provide the model with equilibrium volumes for each feature. So, well, I say for each feature, there's no equilibrium volume for the channel, but for the flood shoal, the ebb shoal, the bypass bar, and the attachment bar, you give the model an equilibrium volume. And then that will be the volume that the model, and you give it a starting volume. And then the model will adjust the transport in and out of each cell so that the equilibrium volumes are being approached as the time goes on. So the fluxes are adjusted as the equation. Like if you look at the equations at the bottom of the screen. So for example, QBA, if the current volume, so VB, is greater than VBQ, then the transport from the bypass bar to the attachment bar is greater than the flux from the ebb shoal to the bypass bar. So that means that you're getting more sand out of the bypass bar so that we're getting closer to the equilibrium volume of the bypass bar. So this is all just pretty straightforward algebra for the inlet reservoir model. So for the general as far as calculating the volumes for the shoaling tool, I think we have the CSAT tool. And that's kind of I think that's a tricky process, but I haven't done as much as I'd like to. But we have some tools down that people work on with NCHL that allow, it's like the coastal, or what is it? The shoaling analysis toolkit, I think. But Michael Hartman, I think, is the one that's the PI on that. So that allows, that's been, I think, a pretty handy tool for people to calculate shoal volumes over the years. Jan, do you know anything more about the shoal volume calculations?
Yeah, I mean that cover most in the practical. I mean, you probably need to gather all the data. If you have hydrotherapy data, then you use the map to identify those higher morpho elements like show bars, and hopefully you can get this volume and volume change. And follow there is one there's one question from Jonathan. He asked us how to determine the equilibrium volumes of an inlet reservoir. Russ, do you want to take that?
Well, that's what I was asking. I mean, I think it's just calculating the shoal volumes.
Mm.
And I think we have Michael Hartman has a tool for that.
That's right. That's right. My experience determining those parameters pretty tough. It's not easy. But ideally, if you have long-term historical data about the morphology change, and you may find the long-term trend of those equilibrium state, then you may use the volume of long-term trend to determine equilibrium volumes. Uh, that's right. Yeah. CSAT, that's the shoreline analyzer tool. If you search for that name uh, through Army Corps, you can get information.
It's a tough thing to assign, Carter.
Yeah, I think if later on if there's an example or something like that, this would help, but it's just having a hard time picturing how. I mean, I can visualize like the channel and the flood shoal and ebb shoal, but assigning a specific volume to that seems sort of arbitrary to me. So I think if I just saw an example of how it's used practically, that would help me um, later on, I guess, during this training.
Come to Buffalo in November. I'm sure it's really alluring.
Sounds good.
Now, another rule of thumb to set up this empirical model, very highly empirical, is I believe this inlet visual model purpose is to provide some estimation of inlet bypassing, so it will able to simulate shoreline evolution across the inlet, so provide capability to simulate the Barrier Island shoreline. However, the free parameter for this model, you can count is totally of 12 volumes. So, if you have a relative stable inlet, then this model behavior probably close to the reality. But if the inlet itself is not mature, it still is changing, maybe harder to handle it. So if it's stabilized, you usually can say the difference of shell bar in scale. Usually, apple shell mostly is the largest element. So you can use your map to estimate the proportional how much change from apple shell to the bar and set up initial guess of other bypass elements. If you have like unit one is apple shell and the bar bypass bar could be uh, 1/4 of that, you can start that kind of estimation. But my experience is bypassing sediment from updraft to downdraft, if it's stable, you can have very clear trend. You have dominate downdraft direction. Then that bypassing may not significantly impact downdraft shoreline change, but it definitely will add on some volume change. Yeah.
So typically when you're using GenCade, you come up with what your alternatives would be, and see what your constraints are as far as like what you could feasibly construct or what your solution will be. Then get your data together. So as you want to get as many shorelines as you can, historical shorelines as you can, and whatever, like you want to get hindcast data from WIS, and then also any kind of interventions that were done in the past. So any structure construction or beach nourishment or dredging. Then develop the model, calibrate the model to whatever historical data you have, validate it. Or check your calibrate it, and then evaluate your alternatives, and then you can look at the results of the various alternatives that you run through. So you might be varying the breakwater transmission or the locations of the breakwaters. groins, just whatever engineering solution you're looking at. The file formats for GenCade, there's a lot of just text files that GenCade runs off of. Once you get used to the model, you can go into all these various input files and edit them manually. Typically, the user at least sets up the model through SMS. Historically, SMS was a little bit slower to run GenCade directly through than to run it through the command line prompt, but I think now that's a little bit, it's no longer a problem. Anyway, but you have your .gen file, which is all your file information, the model setup, structures, inlet speech fills, the initial shoreline file, SHI file. It gives you the cross-shore distance between the x-axis and the initial shoreline for each cell. The waves file, and you can have, theoretically, you could have one wave file for each cell. Typically, it's not the case, but you have one wave file for each wave gauge. There's variable grid shoreline data file if you want a variable grid. So that would be beneficial if you have, say, a groin field, but then you also want to model on either side of the groin field a fairly long ways. You could have refined grid cells along the groin field and then have coarser resolution outside of the groin field. The regional shoreline contour, or it gives you the regional shoreline contour. What that does is that takes the initial shoreline, subtracts out the regional contour, and then that's what is used for calculating the sediment transport for each time step. And then that is added into the final result. So what would happen if you didn't have a regional shoreline and you just ran GenCade indefinitely is it would trend towards just a straight shoreline. So the regional contour is a pretty heavy tool to allow you to modify what the long-term trend of the shoreline will be. And then the water level file, I don't see that used a lot. I think that's only if you're mostly just if you have a variable or variably transmitting breakwater. And so if you need those values, that's an additional file that's required. Here is just, this is kind of a wordy slide, but here is an example GenCade file. You have your title, the location of the files. If you get files from somebody else, you'll have to change some of these things. So the project directory will need to be changed. The initial shoreline file, the DX file, the regional shoreline file, if you're using one, the number of wave gauges, then you have the wave ID that gives you the cell location, the water depth, and I forget what I guess the number of time steps, I think, and then the breakwater, and then the wave file name. All these files need to be in the same directory. And then for the model, the grid setup, we have the XY, the azimuth of the grid, the number of cells. DX of -1 means that we're using variable grid cell sizes. So that's when you need the DX file. And the sim date start, sim date end, DT, your run time step, your save time step, the K1, K2 values. Again, those are the major values that we're using to calibrate. And then we have, so print out, and then whether or not we want to print warnings. iSmooth smooths your contours of GenCade, so it gives you it generally helps with stability, any kind of stability issues. So it's just a moving smoothing window of 11 cells. And then IRAG tells the model whether or not you're using regional contour. Some more. So you input cards, you have your D50. So your grain size, the berm height, and the depth of closure. So any sediment transport you will get will be divided by the depth of closure plus the berm height to get the cross shore or the shoreline accretion or erosion. We have 3 different boundary types: pinned, moving, or gated. And so depending on the boundary types, these conditions will change as well. So you can either specify, if you're specifying moving, you give it a rate. If it's pinned, the boundary stays the same the whole time. If it's gated, that's essentially like having either a groin or a jetty at the end of your model grid. And so that gives you the ability to have transport in or out based on a transmission coefficient. I guess out really. For the output files, we get the biggest one's a PRT file, or no, PRN. But we also get the instantaneous net transport, mean net transport, mean left, mean right. You get the shoreline position file. That's a big one to look at inside SMS. So it's a .SLO file. Yeah, and some of these are not as used. The one I use the most is probably SLO to see that everything is behaving properly. Here's just GenCade inside of SMS. So what you do is you set up GenCade. That's the old slide deck. You set up GenCade with an SMS as like a conceptual model. So basically, you draw all the various features with SMS. So you draw the shoreline, you draw the regional contour, you put the location of the groins and the jetties and the inlets, and then you draw a grid line that represents it's a parallel line from looking offshore, it'd be from left to right, to represent the closest that you could get to like parallel to the bulk of the shoreline. You want it to be, you don't want any really sharp angles in your grid, in your shoreline. And then once you draw that line, then all of the various features that you've specified within SMS can then be transported to the grid, and SMS will create all the various input files for a GenCade run. Then you also need to input your wave events, so you can put in, for the bottom right example, you can see we have the red dots indicate 2 wave gauges that have been inserted in this model. And so you give it a time series for each wave gauge, and then you set up your sediment parameters, and you can run GenCade. So the thing is, with just a typical run of GenCade, you would provide it with a time series of wave events that is determined. And so you won't get any variation in your results. You'll just get one single end profile with a series of profiles in between. That doesn't necessarily indicate what the full range of potential conditions could be. So the goal of the Monte Carlo GenCade application that Jan Ding has been working on is to quantify the full range of potential profiles that could occur in a given in a run. So what the tool does is it sets up input wave conditions for the you give it input wave conditions to determine the PDF for wave heights, period, and angles. Then you generate time series of wave heights and angles based on those PDFs. You simulate those wave heights and angles through GenCade, repeat it as many times as necessary, and then once that's done, you perform a statistical analysis of the shoreline changes to determine the full range of potential profiles. And then that's when you stop. There's a Weibull distribution for our extreme waves and a Raleigh distribution for our normal waves. The Raleigh has a kind of thinner tail that we avoid by applying the Weibel. So we sample from these distributions, and we get our full range of conditions for a time series of, I guess, I think typically 50 years. We did a test case, or Jan did a test case with for the sensitivity to the various conditions, where we had essentially infinitely long groins on either side, so we wouldn't get sediment transport outside of our test. And then just a flat initial shoreline. And so running that through the Monte Carlo model, the maximum shoreline change with the various spectrums was pretty significant in the anyway, sorry, you can have a wide, depending on the order or what waves are selected in the order of the waves, you can get a significant difference in your end result. So here's just some example time series of hourly wave heights and wave angles for this test data set. And we have our history of shoreline positions here. So you can see it fluctuated pretty widely over time. And we have our differing or sample locations at the bottom. And yeah, and the right hand plot shows the various locations over time. And we get, yeah, you can see we get anywhere from, for the observation location at 50, we get anywhere from 35 meters to what, almost 60 meters over a very short amount of time. So you run all the different realizations of the Monte Carlo model and you get the full envelope of potential conditions. So this is 256 different iterations of the model, and you get a full on envelope of the potential conditions. So you get anywhere from, for adjacent to the groins, or you get anywhere from 7 meters of accretion to 7 meters of erosion, just depending on how the waves were sampled. So again, the goal of this is just to give you a good envelope of what could potentially happen. So if you just use a deterministic wave condition, then you're not going to fully capture the full range of potential conditions. So some of these are probably pretty severe in one way or the other, but at least it gives you a good envelope of what could theoretically happen. Now here's just an example at Duck, North Carolina. The computational period was 6 years with a 3-minute time step. You have the wave height distribution, the wave direction distribution. We have a PDF of the shoreline change for various locations. So either to the north of the pier or right south of the pier. The pier here is represented by a non-diffracting groin. Pier introduces a decent amount of effect on the sediment transport at Duck. So you have to account for it somehow. So running the sampled wave conditions from these two distributions gives us a seawardmost GenCade profile after the 50 years, or sorry, 66 years. And then a landwardmost, so you can get you get a full envelope of potential conditions. And then we have our average shoreline, which is the dotted line. It actually follows the seawardmost pretty well. But we get our average shoreline at the 6 here. And that's it. If you need any GenCade assistance, email Jan probably primarily, but I'm also available. Yeah, either one of us really. And but Jan's going to go over some more advanced features that he's been working on, has been developing. Anyway, thanks.